Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is John from Business Review, an NS Media company, and I'll be your host today. It's our pleasure to have PROMECON GmbH with us today, who will be presenting this webinar titled Digital Air and Gas Flow Management for Power Stations. Today's guest speakers are Hans Conrads, CEO and President at PROMECON, and Alexander Halm, Technical Sales Support. I'd like to welcome you all to our webinar platform On24. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click submit. We will allocate some time at the end of the session to address any questions or thoughts that you may have. Please use the yellow help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. But for now, please allow me to welcome Hans.
Well, thank you, Jonathan. Ladies and gentlemen, also a warm welcome here from Barleben in Germany, where we host this webinar for you on our digital airflow measurement systems. I am very happy to speak to a fairly large audience today. I was actually expecting that we are talking to the usual 20 to 40 suspects, but I have heard from our team that we have over 300 attendees to this webinar, so I should say a few words about our company before I really start to talk about our technology. Actually, our company, PROMECON, is situated in Germany, close to the city of Magdeburg, so about 1 hour west of Berlin. And our company has been around for quite some time. We have been founded in 1995, so if you all calculate correctly now, we have been around for 25 years. We have our anniversary year this year, and we actually plan to do a little bit more on trade shows and talk to you people around the world, to our customers and clients. But unfortunately, we're all a little bit locked down like everyone, so we are very happy to have the opportunity for this webinar. And I would like to introduce a little bit of who we are and what we do to all of you, because not every one of you may know us as of yet. Our company is actually it has been specializing in measuring hot and dusty gas flows and also two-phase flows for thermal processes. Thermal process would be, of course, power stations, power boilers, but also cement plants, waste-to-energy plants, as well as the smelter industry. We actually produce measurement systems mainly for flow, but also for the analysis and the optimization of thermal processes. And today, even though our products can be used to increase efficiency, to lower NOx, to increase load flexibility, to optimize electric arc furnace operation, today I would not focus so much on the process, but really on our champion, which is our digital gas flow measurement system that has been installed around the world. The industries that we serve with PROMECON with this technology are, as I mentioned, power generation, waste to energy, steel plants, cement making is a big part of our business, limestone plants, lead refineries, zinc refineries, copper smelters, and even the glass industry. Just to give you an idea of what we have been doing in the past 25 years, here is an example of our installed base for power stations, steel plants, and cement plants around the world. So you can see that we pretty much have been delivering everywhere, and we have clients all around the world. And on this webinar, I've seen that from every part of the world, there are people present. So I hope that you can all hear us. In some locations, it may be very late or very early, but I'll be happy to talk a little bit more about our technology. Today, I'm talking about MCON Air system. It's a digital drift-free vector airflow measurement. It's our base measurement system that most of the customers use. And our system has been replacing conventional technology in many industries for various reasons, which I'm going to talk about a little bit later. First of all, I would like to focus a little bit on three industries that I think are presented in our audience today. The first industry I would like to talk about is the power boiler, so electricity generation by coal. And you can see here the picture of a power boiler, and the typical applications of our system would be the air flows into the boiler, so primary airflow, secondary airflow, overfire airflow, individual burner flow measurement. Then our system can be, of course, used to measure the flue gas into and out of the electric precipitator, also the profile of the flue gas into and out of the SCR or SNCR zones. So even very large ducts can be measured and small ducts. And for power station, the main incentive is to have, first of all, the right amount of air into the combustion as a total flow, but even much more so to have a much better idea of the air distribution from burner to burner and from mill to mill. And this is an undetected problem that I'm going to focus on a little bit later because it's one of the key factors to optimize your plant's efficiency, and this error very often goes unknown. The second area that I'm going to talk about today, at least the measurement for this area, is steel making. And here I have put down as an example an electric arc furnace. Here the situation is slightly different than in a power station. In an electric arc furnace, you have dedusting systems that carry quite large amounts of gas from the smelter bath. And the problem with these gases is not only the dust contamination, but also their temperature. Of course, these gases are cooled down as they go through the primary and secondary dedusting system. However, operators of electric arc furnaces are very interested to know the gas amount right out of the furnace. So right at the so-called fourth hole, they would like to know the amount of gas and therefore the amount of enthalpy that you are losing in the process. Now, the gas temperatures here are around 1700 degrees Celsius, and there is simply no technology around to measure that properly except our technology, which I'm going to talk about today for our listeners from the steel industry. We also may have a few listeners from waste-to-energy plants, which is a big market for us, and here again you can see the gas flows that we are measuring. Starting from the left-hand side, the undergrade air that goes into the individual firing zones of your stoker. And then on the right-hand side, you can see a waste incineration plant consists of more flue gas cleaning than boiler. The flue gas cleaning is the bigger part, and there you have many gas flows that are interesting. The raw gas out of the furnace and the boiler, but then also the raw gas in and out of scrubbers up to the point where we can measure emissions on the stack with an exact measurement of gas flow through the stack. So in all these industries, in these three industries I'm going to talk about and I'm going to address today, we have a big interest to know the gas flow of fresh gas as well as raw gas. Now, before I start with our measurement, I would like to give you a little bit of an idea of what are the typical problems in power stations. And I have to tell you, many of these problems are undetected. If you ask somebody from the steel industry about electric arc furnace, he will tell you, well, the gas is so hot we can't even measure it. So that problem is apparent and it's clear. In a power station, it's a bit difficult because many airflow measurements problems and many airflow measurement drift problems go undetected. And I would like to explain that for a few minutes so everybody is clear on what the problem really is in a power station and why it is so hard to tackle that problem. Most of the boilers have an air heater that is heating up the air going into the boiler so that you recover the heat that the boiler is losing. That air heater is usually a regenerative air heater, and this regenerative air heater or rotating air heater is leaking ash from the flue gas side into the fresh air side. So all the preheated air coming into your duct system as it is preheated will catch up some dust from the firing process. Now, it is easy to understand that this dust in the air will start to give you problems with your instrumentation, the instrumentation that measures your airflow, the conventional instruments that you're using today, the analog systems that you are using. Let me show you how this problem is then manifests itself in your process. What you can see here is a typical location of a secondary air measurement. Yeah, you have an air duct, you have some sort of obstruction in the air duct, such as like a venturi. It could also be an aerofoil. It could be simply an orifice. Now, the way that you measure the airflow traditionally for the past 100 years is that you use the Bernoulli equation. So you simply have an obstruction in the duct, and you are measuring the delta pressure that you are seeing over this obstruction. So you measure the static pressure ahead of the venturi, and you measure the dynamic pressure in the venturi throat section. Typically, this delta pressure is around 20 millibar for venturis. If you are using NU bars or some profile sensors, then the delta pressure is even far lower. You're only looking at 2 or 3 millibar. Why is that important? First of all, you have a squared relationship between the pressure and the flow. That means on your normal flow, you have normal pressures around 20 millibar. As soon as your flow drops to, let's say, 1/4, your pressure drops by the squared law. So for very low flows, you measure nearly no pressure anymore. So the first problem that you have is you do not have a linear relationship between the measured pressure and the flow that you are seeing. The much bigger problem, though, is the dust in the air that I'm talking about. You have dust in your secondary air, and that dust can block the impulse lines that go from your duct to your pressure transmitter. Let's have a look at that. If you block one impulse line, then what you can see is that all of a sudden, you are not measuring the delta pressure anymore before and in the venturi, but you are actually measuring the change in pressure against barometric pressure. The barometric pressure is, let's say, 1013 millibar, so the pressure ahead of your venturi plus the 20 millibar will come up to 1033 millibar. The big question is now, what is your real pressure on the other side of the DP transmitter? Yeah? That is the big question. You will see that your measurement will start to drift, even with a change in weather. If you have a thunderstorm coming or something, and the barometric pressure will drift, your measurement will start to drift with it. And the reason why I'm putting down these numbers is to tell you the order of magnitude. We are talking only about a few millibar of actual pressure that you measure against a barometric pressure of over 1000 millibar. So this is definitely affecting your controls. You are operating a boiler of 1000 megawatts, of 600 megawatts. You are running millions of cubic meters of air through this boiler per hour. And all of a sudden, you are measuring 10% wrong, 5% wrong, 15% wrong. But your operators are usually not able to see this. Your operators are sitting in the control room and they are unable to detect this problem. And I'm going to explain to you why. You can see in this picture that there is a controller which is controlling the dampers so that the air into the boiler is controlled to a set point. If your DP transmitter starts drifting, then the controller will correct the flow to the point, to the set point, right? So the operator who has 20 airflows right ahead of him will see that all the 20 airflows are the same, because the controllers will always control the airflow to the set point. And therefore, the operator in your control room cannot see that all the airflows are basically wrong. They are basically drifting. I've prepared a small diagram that illustrates this very nicely. Yeah? Look at this. You have your damper position, which is the light blue line, and you have the DP measurement, which is the dark blue line. If you now purge your impulse lines and you clean them, which you can see right in the middle, then your calibration for your DP measurement changes. However, the controller will pull down or change the dampers in a way that your DP measurement will end up at the same set point again. So you can see, before and after cleaning, you have the same measurement, but before and after cleaning, you have a different damper position. Yeah? So I'll show you some real-time data from a German power station, brand new, 800 megawatts, T-fired. You can see this is a typical problem. The red line in the middle is the delta P, and the operator sees the delta P before and after cleaning. It has the same value. Now, before cleaning, you will see that the measurement starts to swing and to chase. So the operator sees he has a problem. He sends the maintenance guy down to clean, and afterwards he has the same delta P reading as before. However, the blue line is the damper position. The damper before and the damper after has a different position. So that means the problem that he had was not only a few minutes before cleaning, but it could be down the road for many hours. At the bottom of this diagram, in yellow and red, you can see the PROMECON measurement, which is perfectly parallel to the damper. So the lesson to be learned here is analog measurements like DP measurements drift. Digital measurements like the PROMECON measurements do not drift. They never drift. They cannot drift. And therefore, digital measurements help you to keep your boiler on track. This is problem number 1. Along with problem number 1 goes swinging of the flow, because the clogged impulse lines, they are delaying your control, so you start to get swings in your controls. And this is also a problem that will not occur if you don't have a drifting signal, which you have in analog systems, but in digital systems you do not. Now, here's another thing that needs to be discussed. You can see a manifold, as you can see on many boilers. You have a header, and in this picture, the header is coming out of the picture, right? So the airflow, that blue, dark blue square on the lower bottom of the picture, that airflow is coming towards you. It's coming towards you. And as it reaches the manifold, it then branches out into the 5 individual ducts. What do you see on this picture? You see that the middle duct has a fairly straight flow. Now, if you look at the 2 ducts left and right, you can see that these ducts have a swirled flow. And that is, of course, that is the consequence, because the air goes not only round the bend upwards, but it also goes sideways. And this bend in 2 dimensions, upwards and sideways, causes the air to start to swirl. Because of the inertia law, the air wants to continue to go to sideways, but it can't, so it starts to swirl. So, most of your ducts that you measure in a plant, behind an ID fan, behind the FD fan, behind bends, most of the ducts will have swirled airflow. How do you measure swirled airflow? That's the second big problem that we're going to address with our PROMECON measurement today. So, how do we cancel these? How do we attack these problems? We have drift and we have swirl. First of all, our measurement system is working much different from a delta P measurement system. The PROMECON system works by the electrostatic correlation of time of flight. How does that work? First of all, we generate a raw signal from the dust that is carried along in the gas flow. So we don't have a problem with the dust as a congestant, but the dust is more or less our friend. It's our tracer that we use to detect the gas flow. The way that's done is that you have a sensor inside your duct, and that sensor is then surrounded by the electric dust around it. The dust that goes through the pipe is always charged with a slight electricity on the top of the surface of the particles. So you have clouds of positive charge and clouds of negative charge. Now, the cloud that is surrounding the sensor will automatically induce a negative or an opposite charge on the sensor itself by Coulomb's law. So if you have a positive cloud going by the sensor, you will see a slightly negative charge on the antenna, and vice versa. So as the clouds of particles fly by the antenna, you can see an electrostatic charge signal, which is actually showing you the pattern of the clouds flying by. We call this a time signature, right? So you can see in the succession of the current that you measure how these clouds fly by your sensor. The whole measurement principle now uses the fact that you need two sensors to measure, a first sensor and a second sensor. And the correlation algorithm between sensor 1 and sensor 2 will give you a best match at the time of flight between the two sensors. So how does it look like? You have two sensors and a box. You can see also how this is mounted in a duct. You mount them in the direction of gas flow, right? So it doesn't matter if you have a lot of dust or little dust. You mount them in the direction of gas flow, and the dust flying by on the sensors leaves a signature on the sensors. So you have the signature on the sensors, sensor 1 and sensor 2. And you can see with your bare eyes that these signatures are not the same, but they have a very big similarity. And this similarity is what our correlation algorithm is detecting. We are detecting similarity between signals. This is very, very, very important, because this is what makes this measurement digital. We don't care how big the amplitude is of a signal. We only care if it's similar to the other, right? So let's put them on top of each other and see how similar they are. You can see these are the two signals. They are similar, but they have a time shift. They are not the same. So what we do now is we take those two signals and we put them into a cross-correlation filter, and we get the cross-correlation function. The cross-correlation function gives you a maximum at the time shift where these two raw functions have the biggest match. So we see a time shift, in this case 52.1 milliseconds. So what our measurement does, it has a digital clock, and all it does, it gives you a time shift every second. So every second you get a new value for time shift. Now, if you take the distance of the sensor and you have your time shift, then time shift and distance of the sensor gives you velocity. So our system is a gas velocity measurement system, right? So this is the primary measure that you get from our digital flow system. And the characteristics of the typical electrostatic system is that you can measure up to gas temperatures of 1,000 degrees Celsius. You can measure gases that have no dust up to 3,000 grams of dust per cubic meter. You can measure in the typical accuracy if you have a good flow pattern of a few percent. You measure at a very high repeatability and absolutely no drift. Right? So these are the main characteristics. And as you can see on the left-hand side, where in a delta P measurement you need to purge and clean from time to time, and you need to recalibrate, you need to re-zero, all this is gone with the MCON Air digital measurement. You put this measurement in, and then you can forget it. It will measure accurately throughout its life. It will not drift, never. And as mentioned, you can also get our measurement as a SIL2 credited system according to EN 61508. So safety integrity level 2, that's usually the standard or the demand for new boilers if you want to measure purge air in a boiler, or you have any other safety relevant application where combustion air is critical. Now, I was talking about the distance of the sensors. The distance of a sensor is a very interesting and important feature of our system. Why? I have mentioned to you that one problem is the drift because of the dust. The other problem that I've mentioned is the swirl. The swirl means that you do not have a straight flow over your sensors, but you have a flow that has a lateral component, right? So the flow does not go over your sensors in a perpendicular or orthogonal way, but it can flow in some sort of direction, sort of like this, right? So what kind of velocity are we now reading? What kind of velocity is our MCON Air measurement reading? Well, our MCON airflow measurement system is calculating with this distance of the sensors, right? So the distance that we assume is the vector that's orthogonal on both sensors. And this is extremely important. The PROMECON system only measures the flow vector that is perpendicular to our sensors. We don't measure any other component. So when you have swirl, we don't see the swirl. We only see the vector that's perpendicular on our sensors. Very important point. So the correct velocity is only the one in the direction of the longitudinal axis of the pipe. PROMECON have a special system which is also built into co-burners, where we put two sensors on the burner barrel. And as we sit downstream of the swirl element, we have a huge swirl over the burner barrel. But these two sensors are only sensing the velocity along the burner. Now, this is also important, for example, for stack applications. If you look into a stack, you have an ID fan, and the ID fan will always swirl up the air through the stack. Even if you're high elevation, you will have some sort of swirl that goes through the stack, and that needs to be measured. Now, our sensors will only measure the vector that goes right up the stack, and they will not see the swirl. We just have received a certification for our stack flow measurement by the Deutsche TÜV, and we are quite fond that the TÜV mentioned to us it is the most accurate stack flow measurement that he's ever certified. And you can see that on the TÜV page, TÜV Süd, the QAL1 certification. There are the accuracies of all the emission monitors that have been tested in the past years from all the manufacturers, and the one that is PROMECON is the highest accuracy. Now, I mentioned to you a few minutes ago that we can measure from 0 milligrams of dust. Now, some of your people might have asked themselves, if there's no dust, how do you measure the gas flow? PROMECON has invented something that is called the range extender. The range extender is a rod that is mounted upstream the sensors. And this range extender ionizes the gas with a small pulse of electricity, a little bit like a spray electrode in electric precipitator. Now, this ionization will also go over our sensors, and it will leave a signal on our sensors so that we can also measure the gas velocity with this ionization. Where is this ionization necessary? We recommend it for all power applications, because sometimes when you start your boilers, you run with very low air velocities, and when you start a mill, you sometimes run with clean air. We recommend the range extender also for batch processes, when you sometimes have, let's say, a deducting system in a steel plant and you sometimes run clean air. So the range extender extends your range of dust that you can still measure, but it also does another thing. The range extender allows our measurement to measure not only from, let's say, 8-9 meters per second, but to measure down to 3 meters a second. So now our measurement can measure from 3 meters per second up to 100 meters per second. And it is completely linear. So the turn-down ratio is very big, and at low velocities we still measure very accurate. And this allows power stations to measure, for example, burner cooling air, to measure exactly the amount of air that goes through switched-off burner rows. And that allows you to have a much tighter stoichiometry over your boiler. We also measure creeping air from dedusting systems, canopy systems in the steel industry. So the range extender is a big asset to our measurement for the extension of the flow range. Here you can see typical signals of the range extender. You can see how this is usually working. Picture of the range extender. It's just a rod that you put in, a couple of spikes at the front to be able to discharge the ions into the gas flow. Okay, some technical features of our measurement. This is how the measurement looks like. You have a small box and 2 sensors. That's the basic setup. There's also an extended setup where we measure temperature in order to make a compensation of the volumetric flow into standardized gas flow. And if somebody wants, you can also measure the static pressure. In most of the thermal processes, however, the static pressure is basically the barometric pressure. So the temperature has the biggest influence on the gas density. And you can either measure the temperature separately and then calculate all this stuff in your DCS system, or you can also calculate it in our box. That's everything you have. You have a small box, you have a couple of sensors, and out comes a 4 to 20 milliamp signal and system fault. Now, I have not spoken about electric arc furnace, and I have not spoken about high temperatures. We have a lot of clients in the world that use electric arc furnace, and they are very, very interested in our sensor. We have lots of clients, Tinova, Mittal, Arcelor, in the US, all over the planet actually. What these people have been complaining about is the fact that they cannot go to the electric arc furnace right to the 4th hole. The 4th hole is exactly the opening that comes off the smelter bath. And for many electric arc furnace operators, it is very, very interesting to understand how much enthalpy they are pushing out of their electric arc furnace into the stack. For this, they need to know the gas velocity. Now, how can you measure gas velocity at 1700 degrees C? This, of course, is impossible with electrostatic measurement. So PROMECON, in the last years, have developed a system that uses infrared light emission of the gas from the electric arc furnace, and we correlate the 2 light rays the same way that we correlate the electrostatic signal, right? So what we do, we look into the process from one side only. It's a passive system. Nothing looks into the process. And we can, from that, calculate the velocity that comes out of the 4th hole directly into the dedusting system. This system has also been used in power stations that burn lignite coal. Power stations that burn lignite coal very often have so-called beta wheel mills or ventilation mills. They pull flue gas from the top of the furnace section, 1000 degrees Celsius, high dust level, right into the beta wheel mill. And these power stations are very interested to learn the mass energy balance of their mill. However, this is very difficult because the hot gas flow into the mill cannot be measured online. No measurement can survive. Now, our infrared measurement has been tested in German power stations, in several power stations over a long time. And it has proven to be very reliable, and we can measure now 1,000 degree hot flue gas from the top of the boiler into the beta wheel mill. So this measurement is very good for this special power station application, as well as for any steel application or smelter application on hot furnaces. We also have applied this measurement in a steel plant in Austria on a BOF, on a basic oxygen furnace, where the user also wanted to know the amount of flue gas coming off his BOF. So it's a very well-suited measurement for the smelter industry. Here you can see how it is applied. You have two flanges. The two sensor heads go right on the flanges, and that's pretty much it. The sensors themselves are cooled with nitrogen because we have very high temperatures right on these ducts. And the openings that we need for the sensors are usually 25 millimeters times 5 millimeters. So if you have a small gap between two water pipes that are cooling the hot gas on a fourth hole, a very small opening is enough. So we need two small openings where we can fit our flanges to and then mount our sensors onto that. Again, I would like to sum up the motivation. Why do you want to install the PROMECON measurement system? Well, let me start with the steel and smelter guys and the cement. Everybody who is in this rough industry has no gas flow measurement that works. So for all these rough industries, I think our measurement is the only choice that can be used to measure enthalpies, flows, etc. For the power stations, the typical power stations and waste incineration plants that have delta P measurements, you are suffering from blocked impulse lines, and these blockages cause long-term drift of your signals. And because of the fact that your measurements are all controlled by dampers, your control system will always control your signals to a set point, and therefore your operators cannot really see what's happening. Let me tell you a story from India, because I'm sure I have a couple of Indian listeners. I've been to many Indian power stations, and what the operators have been telling me over and over again, they say, "Sir, if we switch off automatic control, the whole system, the whole boiler runs much more smooth." Why do you think they tell me that? They tell me that because the problem is not the control of the boiler. The problem is the measurement of the airflow, because the measurement is drifting and jumping around and unstable. Everything in the boiler is swinging. Everything in the boiler is not as it should. And only if the operator starts to switch it off, he can get some more stable operation. The price that he is paying, though, is he is not running his boiler at his optimum air setting, so he's losing a lot of efficiency. And the other big price that he's paying, any load change is a nightmare. Any mill load change is a nightmare. Starting a mill takes forever. Making changes takes forever, because it takes a lot of skill and a lot of knowledge to do these changes by hand and by damper instead of a control loop and a reliable measurement. So here's my invitation to all power stations in the world. Please join us in the 21st century and make your airflow go digital. Go away from analog, go digital and drift-free. So, a little bit of an overview. How is this system set up? You can see in this picture very nicely. You have your duct with your two sensors on the bottom of the picture. You can have the range extender on the left-hand side of this duct prior to the throat section. Then you have the range extender control box, and you have the MCON Air seal box. This is all part of our scope of supply, including the sensors. And then you have the energy supply, which can be 24 volt DC or 230 volt AC. In fact, our AC supply is a wide range supply, so it can be anything from 65 volts to 240 volts. And it can be 50 hertz and 60 hertz. We are talking to the whole world on this webinar, so if you have 60 hertz, it doesn't matter at all. And then, of course, it goes all out to the control system, the 4 to 20 milliamp signal, and from there it goes into the DCS control loops. So very simple, straightforward measurement. You don't need impulse lines, you don't need purge lines, you don't need any of the plumbing that you've had before. Only the two sensors and the control box is enough. Let's look at a few installations. This is a 800 megawatt Alstom boiler, ultra supercritical, latest state of the art. You can see the sensors from the inside of the duct. On the left-hand picture, you can see the duct from the inside. You can see the range extender in the front and the sensor in the throat section. On the right-hand picture, you can see the whole thing from the outside. So our technicians were so nice to crawl into this and have a look. This boiler had everything equipped with delta P measurement, and after it went into operation only a few years ago, they noticed they have a drift problem, and this boiler has completely replaced all of their delta P measurements with our measurement. This is a Chinese boiler. It's built by Harbin. Also, this boiler has delta P measurements everywhere, and it's located in Turkey, and the Turkish client had such a big trouble with this delta P measurement that they replaced everything with a digital measurement from PROMECON. Primary air, secondary air, everything. This measurement location is from a Mitsubishi Hitachi boiler, 800 megawatts, ultra supercritical in Germany. Mitsubishi Hitachi put our sensors in from the start, so some of their boilers were equipped with our digital airflow measurement from the beginning of the erection. 2 or 3 boilers in Germany were not equipped with our stuff. They were equipped with delta P measurements, especially the boiler in Wilhelmshaven and the boiler in Rotterdam. And these boilers are now replacing all the delta P measurements as well with our digital flow measurement. So all the ultra supercritical boilers go digital. Some certificates of our clients. We have, of course, a lot of client letters. These are certificates now of the norms and standards that we fulfill. We can give you a list a little bit more detailed than that. And last but not least, I would like to go through the technical details of the box. This is our measurement box that you can put onto your system. You can see here the measurement range. This is 0 to 100 meters per second. Yeah. Many clients ask us, how many cubic meters of per hour can you measure? That is simply a function of the size of your duct. And I'm sure I will get some questions from you on duct sizing and duct location. That is, of course, a very important point. When you have a large boiler, usually you have no straight run where you can put this. So here, PROMECON will help you to spot the ideal location. If you have existing venturis, existing airfoils, any change of cross section in your piping, then this is a very big advantage because any venturi, any tapering of your duct down to a smaller cross section is a flow straightener to your flow. So if you have an existing venturi, even if the standard says you need 5 or 6 D straight run upstream the venturi, that is correct because you measure the pressure ahead of the venturi and in the venturi. But for PROMECON, we only measure in the throat section of the venturi. We don't care about the stratification or the gas layering ahead of it. So for us, it doesn't matter, and therefore, if you have existing venturis, it's an ideal location to measure. Here you can see the spec sheet of our sensors, the seal sensors, and the range extender. So these are the boxes. We are happy to send you some of that. And last but not least, this is the spec sheet, brand new, of our new infrared sensor that can go onto very hot applications that so far were impossible to measure at all. So for the smelter industry, I think that this will be a new age where they can be able to measure their losses out of their smelter bath directly. And also for power stations that are using beta wheel mills, we can then control the beta wheel much, much tighter. We can control any changes in the filling level of the beta wheel mill much more early, so the mill doesn't drop out and doesn't drown. So this is pretty much the end of the presentation. I hope that you have gotten an impression of digital technology and what it means. I think there are so many aspects in your plant, regardless of which application we're talking about. Usually you can go on to talk about applications forever. This was meant to give you a first splash, a first idea of what is possible with digital measurement technology today. We have thousands of these installed worldwide, and we hope to have many, many thousand more in the future. I believe that this sort of measurement for thermal process, gas flow, will become a standard measurement in the next 10, 20 years, because the advantages to conventional measurements are simply very, very, very big. And this basically ends my presentation session. I will be here for you for another 15 minutes and be happy to take your questions, and I will answer as much as I can. Thank you.
Perfect. Thank you very much, Hans. So just a reminder for the audience, in order to ask questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click submit. So we already have some questions that have come in. The first being, what are the minimum and maximum of duct sizes for the measurement?
Yes, this is of course, this is the first question, very important, very good question. I have already mentioned slightly what the points are. Whoever put this question is thinking in a classical way. We have a straight duct, we have an obstruction, and how much straight run do I need? The usual 3-5D that you have on a Venturi, we don't need. The very important question here is, how big is the reduction in cross-section where our measurement is? So for example, if you have a straight pipe, no reduction, then of course you will need several diameters of straight run so that our measurement can measure with one pair of sensors. If you don't have this, then of course we can use several pairs of sensors and do the average of what we are seeing. So we also can measure with a smaller inlet section. The best thing, of course, is if you have an existing obstruction, such as an aerofoil, as a Venturi. In this case, we can live with a very small inlet section. If you are in doubt and you have a large project, we will be happy to assist you if you give us a drawing of your duct, and we can then have a look at it and give you a recommendation of what you need to do to have an accurate measurement at that location.
Perfect. Thank you very much for that, Hans. So we have another question here. Is it possible to use the measurement in ATEX zones like ducts with pulverized coal?
Yes, we have one measurement that we have is for the measurement of coal flow, and in coal flow we're measuring both. We're measuring the velocity of the primary air, the dirty air, right? So we can measure how fast the coal is flying out of the mill and into the burner. On top of that, we have a measurement function that allows us to measure the density of the coal. So we can even measure the mass flow of the solid of the coal. This system is called MCON Coal, and that system is also certified for ATEX. I have not been talking about the system here, but it's a system that we have also installed around the world in many places, also in many new plants in India.
Perfect. Thank you very much for that. Don't forget, you can still ask questions via the Q&A widget in the top left-hand corner of your screen. So we have another question here. Do you have any application on turbine exhaust gases in paper mills?
We have worked on exhaust gases quite a lot. We have not done it for paper mills, but I don't think that will be a problem for us. There are two big things that we see as an advantage of our measurement. The first one is that we can measure, actually there are three ones. If you're talking turbines, we can measure at very high temperatures. The turbine usually has about 500 degrees or something like that. The second one, of course, is that we don't see the swirl. So the swirl that you get out of your turbine is something that will not influence our measurement. And the third one, of course, is that we can measure at very high velocities. So so of course we have not measured so far at supersonic, but if you have a velocity of 100 meters per second, that should not place an obstacle to our measurement. So we are quite happy to look into such an application. We would ask also here for a drawing or a sketch so we know roughly what the dimensions are and the velocities that we're talking about.
Perfect. Thank you very much for that. So we have another question here. It reads, 3D, 1D inlet diameter, can it be shorter if we have a flow adjuster for more laminar flow inline?
Yes, it can definitely be shorter, and I've talked about that. If you reduce the cross-sectional area, you can be shorter than 3D. But for that, I would like to see a drawing, and also I would need to know the flow velocities. As you can imagine, if you have a very low flow velocity, then the flow straightening effect is lower than if you have a higher flow velocity. So, flow straighteners will help a lot in getting our system installed.
Thank you very much for that. We have another question here. For clean air measurements, is it always the range extender required?
Yes. For clean air measurement, if you have an absolutely clean air, then you need a range extender. Now, clean air there's a nice definition. What is clean? We have, for example, bunkers, waste bunkers in waste-to-energy plants, and in many of these, the air is so dusty that it's not clean. So we would have to have a look at how clean it is, but if it's absolutely clean and cold from outside, we would recommend to have a range extender for combustion air.
Thank you very much for that. We have another question here. Will swirled air not cause loss of any pattern match?
That's another very good one. Yes, it will at a certain degree of swirl. I don't know if you remember the picture of the burner flow measurement. There was a picture of a burner flow measurement that I've shown you where the two sensors are mounted on a burner barrel. And if you look at that picture, you will see that the two sensors are not behind each other, but they're sort of offset in the way that the flow goes around the barrel. Now, this is done because you have to catch the pattern that went by the first sensor, also by the second sensor. So yes, you have to make sure at a certain swirl that you still catch both patterns. However, in a normal stack situation, in a normal duct situation, in a power station, this is not a problem. It is a problem on burner barrels. It is also a problem on the outlets of cyclones and on the outlets of classifiers of mills if you have a big cement plant. So there are situations where you don't mount the sensors in line, but you mount them slightly offset. But the trigonometry is the same. You still get an accurate vector reading for your flow.
Perfect. Thank you very much for that. So we have another question here. Is this flow meter approved according to QAL1 for emission measurements in stack?
Yes, it is. And that's a very short answer. Let me add to that. We are quite fond because it is the most accurate ever approved QAL1 by TÜV Germany. So if you look at the page, you can see it's an accuracy of better than 1%, which no one else has. Yeah, we just got our QAL1 about a month ago, and so it can be used on stack.
Great, thanks for that answer. We have another question here. Which is the range of temperatures the new MCON Air-IR can work at?
We start at 300 degrees C, and it ends actually at 2000 degrees C. However, we had not had these temperatures yet. We've done up to 1700, but 2000 is no problem. That's the range of temperature that this thing is designed for.
Great, thank you very much. So we have another question. How much obstacles will affect the flow measurement?
How much obstacles? Okay. If so, I have to think about what the obstacles are. These obstacles can probably be beams inside the duct. If you have old power stations, sometimes they have beams inside the duct, they have obstructions. In this case, just a single beam that goes across the duct will not necessarily be a problem. If there are bigger structures inside the duct, we would like to see a drawing, and we could then have an assessment of in how far that will really affect your measurement.
Perfect. Thank you for that. So we have another question. Does the coal flow measuring device work with biomass?
Yes, it does. We have installed it at a power station in the Netherlands. We have installed it at the largest biomass power station in the world, at Drax Power Station in Selby. We are currently working with them to optimize their combustion. Cannot tell more details than that, but we started with one boiler a few years back, and this year we have completed the 4th boiler of complete biomass flow measurement. So all 4 units at Drax are now retrofitted with that. We have done a complete boiler in the Netherlands years ago in Gelderland Power Station, where we're also our measurement was used to control the biomass added to the 660 megawatt boiler. So there are not so many biomass plants, but the ones that are around in Europe, we have seen quite a few of them.
Perfect. Thank you very much for that. So we have another question. For burner barrel, is it possible to install both range extender and sensors?
Yes, the range extender. If you have a burner barrel that sits basically, you only use this if the burner is sitting in a wind box. If you have an individual secondary air ducting, then you don't need that. But if you have a burner that sits in a wind box, which is very common, then you measure with our sensors right on the burner barrel. But the range extender is usually outside the barrel. It's really close to the shroud or the register where the air goes into the burner. So that's usually the setup that we have tested. And so the range extender would go into the wind box from the outside, and the sensors would be welded right onto the burner barrel, and then the burner barrel would be mounted inside the wall, the boiler wall.
Perfect. Thank you very much. So we have another question here. If we change fuel from gas to diesel in a gas turbine, i.e. different particulate levels, do we need a new setup of the MCON Air?
I don't think so, because we have quite a different range of fuels also in boiler applications where we have tried this. If we're talking also on a gas turbine, there are 2 possibilities. You can have the possibility of measuring with the electrostatic device, but you could also measure with the infrared device. It's also possible. And you can measure with gas and with oil alike. There should be no problem with that. So I think this is okay. You can use both fuels.
Great, thank you very much. So we have another question here. What is the maximum dust load for the measurement?
Very high. We have measured flow velocities up to 5 kilograms per cubic meter of transport air. However, there's one thing that you have to understand. Our dust levels can start from 80 micrograms per cubic meter or 60 micrograms without the range extender. If you have a range extender, they can go down to absolute 0. And the maximum level, as I mentioned, is a few kilograms or a few thousand grams per cubic meter of air. However, at these high levels, there will be a segregation of solid versus gas flow. So you can see a slip between the solid velocity and the gas flow velocity. That's something that you need to keep in mind. But I would say anything up to grams, so many grams per cubic meter of fine dust should be very accurate in terms of gas flow measurement.
Perfect. And we have time for one more question, and it reads, can I have the flow checked multiple test points, locations, and use only one set of sensors?
Yes, it's a very important question. What we need to what we need to check is the geometry of the duct that we want to measure. If you have a long duct and you have a good geometry and you have a fairly flat profile in your duct, yes, we can measure with one pair of sensors. I give you an example. The company MHPS in Maasvlakte, they have tested all our measurements in the duct with a grid measurement of a SP tow tube. And all the measurements were very well in the accuracy requirements of MHPS on over 60 measurement locations. If you are measuring directly behind a bend or you have a very big stratification in your flow, then we have to see what can be done in order to make a good accurate measurement. Either you put in a flow straightener or you put in several pairs of sensors and you average the flow. So that is then the thing you have to do.
Perfect. Thank you very much. And thank you very much, everyone. And just a reminder, if you didn't get your question answered today, they will be available to be answered in the coming days and weeks. So that just leaves me to thank Hans and Alexander for what was a great presentation, and to PROMECON GmbH for sponsoring this session. To the attendees, you will receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. We look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned, and follow us on Twitter at BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. Thank you all once again, and I hope you all have a very nice day.